I'd like to talk about thermal processing and computational model that we developed. First, I'd like to introduce the organization that I belong to. Toyo Institute of Food Technology, TIFT has been handling packaged food for about 62 years. Our founder, Takasaki, is the same person who established Toyo Seikan Group Holdings in 1979. They have been producing general packaging products for food or beverage manufacturers for over a century. Hiroshima University was established in 1949 as a public university in Japan. Now, let's consider the main issues. Using advanced computational method, everything can generally be modeled and calculated. For example, the accuracy of the weather forecast has improved dramatically, and holiday planning has gotten significantly easier. Moreover, it's crucial for packaged food manufacturers to model internal temperature distribution in containerized food products. This will help them identify heat degradation identifiers in food properties and optimize ambient temperature patterns for thermal processes and packaging design. These are the products, example of plastic cup products in Japan over the last 20 years. Plastic cups have been several features. They are easy to open, microwavable, and soft and safe. Our target is plastic cupped food for retort, which is increasing in popularity. However, the existing computational model have mainly been developed for metal can and retortable pouches. And they mainly evaluate the temperature in the central region, known as cold spot. They also lack precision of the temperature distribution of plastic cupped food, likely because they haven't not considered two effects. One is container material and other is a thermal boundary layer, or tBL. First, the employed model neglects container materials effects. The plastic material for retort is relatively thick and they have lower thermal conductivity compared with the material of metal cans and retort pouches. Therefore, the heat flow across the wall is lower for a given temperature gradient. This is the main reason why it is critical to consider the container material. Second is tBL. This illustration shows a steady heat conduction model of heat exchanger. High temperature fluid flows upward. Low temperature fluid flows downward. Constant heat flows across the solid partition. The temperature profile near the solid partition looks like this. There is a difference between fluid and solid partition. The effect is called a surface heat transfer coefficient. It is representing H. The H value is representing the property of the tBL. And this table shows that H depends on the heating medium and flow condition, resulting in a range of H values. This table shows the relationship between the container and heating medium. Multiple layers multiple reproducible methods are used for plastic cups, and therefore their various heating mediums are conditions resulting in the various thermal property of the TBL. This is the main reason why the TBL should be considered. In this research, we use the water immersion type retrieval method because the heating medium doesn't need to be changed, just water. To address the challenges, we aim to develop a computational model accounting for container material and TBL to simulate temperature distributions in cylindrical plastic cups containing 6% gelatinated starch during their retrieval processes. Next, I'd like to introduce the subject of our research. This is a general cross-section of the subject. Plastic cups were considered, which were geometrically shaped like a cylinder. The thickness of the wall and the bottoms were almost same, using three thicknesses, 0.5, 1.0, and 2.0 millimeter. A 6% gelatinated starch was fully filled. Then the cups were sealed with lit film of 0.1 millimeter in thicknesses by heat sealing. Return to test starch after the whole cupped food cooled to room temperature. The temperature was measured at multiple points along the height and radius directions. Return conditions. We used the water immersion type. The return condition was 120 Celsius degrees for 30 minutes. Every test was conducted with the same condition. The heating process was consist of two periods. One is zone 1, heating process, heating 17 minutes. Another is the zone 2, rotation period of 30 minutes. Cooling process also consists of two periods. Zone 3 is the cooling of 26 minutes. Zone 4 is the retention of 30 minutes until all locations are below 40 Celsius degrees. This is a computational model. The gelatinated starch was inside the cup and lit film, which is covered with 4 millimeter thickness of the TBL. The measured reduced temperature was set on the surface of the TBL model. The TBL was handled as solid, and the TBL include the surface heat transfer coefficient as the thermal properties and it was determined by trial and error. We use the same value throughout the whole computing process at every case. The container material is assessed by electronic balance, TMA, DSC, and guided heat flow meter. The model thickness were fixed at about 4 millimeters to reduce calculating time by cutting the number of the model elements. For example, when the cup wall thickness was 0.5 millimeter, the heat conductivity was multiplied by 8 times. That of the unstudied heat conductivity equations were used according to computational fluid dynamics. Here is an example result of predicted values distribution, temperature distributions in the height directions of 2.0 millimeter cups. The left side is the heating process and the right side is the cooling process. This upper figure shows a cross-section view of previous model. rotate 90 degrees. In the lower figures, the horizontal axis is the measured location, which is referred to the distance from the bottom of the cup. In this figure, dot represents the measured. Red one is return to temperature. Black one is the starch, which is measured in each location. Line represents the predicted one. The red line represents the tBL. The green one is the container material, and blue dashed line are the starch of each location. Starch. During the heating process, the starting point is this. After 5 minutes, the temperature distribution curve changed like this, and 10 minutes, 15 minutes. In the cooling process, the starting position is for 5 minutes, that of the same 45 minutes in the heating process, and 50 minutes and 55 minutes. In these figures, the most dots are located on or near the prediction lines. Ultimately, the deviation of the temperature distribution between thin lid and thick bottoms are well modeled. Let's discuss the F0 values. This graph shows a comparison of the measured and the prediction F0 values in the height and radius directions. The blue bars are the measured and red ones bars are prediction of the F0 values. The maximum difference between the measurement and prediction was 3.4%. These are the quantitative comparisons using RMSE. RMSE is the root mean squared error, which is defined by this equation to use to compare measured and predicted temperatures. These upper figures are the height direction. Lower ones are radius direction. The left side figure is the RMC is a function of the elapsed time. These retention processes is the sterilizing process, which is hold on 120 Celsius degrees, which is very affected the quality of their highest temperatures. These upper right figures are the RSME is depend on the location of the height. In this lower figures, the RSME is depend on the location of the radius. The maximum RMC was approximately 4 Celsius degrees, and remarkably, the RMSC during retention was under 2.6 Celsius degrees. In conclusion, we developed computational models accounting for the container material and the tBL to simulate the temperature distribution in cylindrical plastic cups containing 6% gelatinated starch during the retort processes. 1. The maximum difference between the measurements and predictions was 3.4%. The maximum RSMA was approximately 4 Celsius degrees, and the RMSC during retention was under 2.6 Celsius degrees. This study demonstrates the efficiency of the model that integrates tBL, containers, and contents, suggesting its capability to predict temperature distributions in containerized food products during retort processing. These are the future issues. First, there is the matter of the thermal property of the TBL. Now, it's determined by trial and error, but in the future, it should be determined at once. Second matter is the color verification. The browning index cooking value CB is calculated using this equation with the D value of 25 Celsius degrees. In the future, we need to compare the real browning degrees with the predicted CV after result processing. This is an example result of the predicted CV cooking value. Browning likely occurs at these areas, including blue stars, near the surface of the container. However, it is difficult to measure these temperatures precisely. This curve shows the predicted CV in the radius direction. Blue represent the thickness, cup wall thickness of 0.5 millimeter. Red one is 1.0. Black is 2.0 millimeter. In the prediction is, if the prediction is precise, then we can reliably simulate the result conditions on the computer. Thank you for your attention. Are there any questions?